the record. Okay, I think
Yes,
it's recording.
Yeah, it started.
Okay, then let me share the screen again.
Lets you see everybody in the big grid only comes up after a certain number of people, because when you went away, Don, so did the view of everybody, and when you came back, it came back. Is this the same program that Akram used?
Who used?
Akram.
Akram. Who is
that? Okay, so she was the woman from Iran. She's working for Iris now.
I'm not sure.
Bob, I think Akram already left before Jiayan came in.
Maybe, yeah. It's my first time to hear this name.
All right.
Okay. So I'm not sure if is there any news. Okay, so yeah, let's start. Okay, hello everyone. Thanks for joining this talk. So today is my turn to introduce a software which is called SpecFEM3D, and I will introduce how to use this software to simulate the synthetic waveforms. And there are two different versions. And today, this version I want to introduce is Cartesian version. And there, if you want to simulate waveforms for global model or larger models, then there's another version called SpecFEM3D Global, and it's also available online, but I didn't use that version before. So let's focus on this version. And so this software can be used to simulate synthetic waveform, seismic wave propagation at a local or regional scale, and you can do a lot of work like to adjoint tomography, calculate sensitive kernels. I'm still learning these programs. So yes, it can do a lot of works. And it's also very suited to parallel implementation of very large supercomputers. You can call many processors to run a code, and it will save a lot of time. So here, there are two links you can use to download the code, and you can also find more details from the manual of this program. And if you want to install the code on your computer, here are two steps. You need to run two commands in the terminal window. This is the first one command, and because I installed this program on the HPC of our university. So the compiler I used is Intel compiler iFort and ICC. There will be an arrow show up if I just simply type this command, because maybe the HPC cannot can't find the include directory of the iFort. So I modified this file and passed the directory of this include folder into this file, and then it will generate the make file, and then you can tap the make to install this code. So if you want to simulate synthetic waveforms, there are three steps you need to do. The first is mesh generation. You need to build a velocity model. And second is creating the distributed database. And the third one is running the solver for synthetic waveforms. And the structure of this program is it has many examples in the root directory of this program, and I built a test folder in here, which includes 5 folders in this test directory. The bin folder will include some compiled files, and most parameter files was included in this data folder. And this database MPI folder has the output, and also output files will have some part of other outputs of this program. And if you just need simulate synthetic waveforms, You don't need to care about this folder. This ref sys folder is used to include the observed data, which is used to for the like ageoentomorphy, that kind of stuff. So let's go to the first step, how to generate a mesh. So there are two ways you can use to build a mesh. First one is called meshing tool called Qubits, and it works for this program. Can build some finite element meshes. But it can be purchased for small academic institutional fee. Here is a graphical interface of this software because it's not free. So I didn't use this software before. And it's an independent software. You maybe need to install this on your computer. So as an alternative tool, this program has another tool called XMesh FEM3D. So it's an internal tool in this program. You don't need to install it again, and it can be used to build relatively simple models. So to build a model by this XMesh FEM3D, you need to have this mesh FEM3D files folder in the data directory. So in this folder, there are 3 files you need to give. You should give to this program. So main parameters will be set in this mesh par file, and there are some other files or 2 or more files which describes the shapes of the interface. So if you have one interface, you need interface 1.data. If you have more interface, maybe you need more like interface 2, interface 3 data files. So let's see the mesh par file first. And so you need to give some parameters to define the range of your model. So first 4 parameters: latitude, minimum latitude, maximum latitude, minimum longitude, and maximum longitude will limit the range of this model. And depth block, this parameter see the depth of bottom of your model. And the first 4 columns in here, the unit of them is degree. And for the depth, this unit is kilometers. And then you need to give a UTM projection zones, which to transfer your model from a Cartesian system into this global systems or geographical system. And so you need to find the UTM projection number, zone number. For example, in here you need to use 3 for American, and also you should use the indicative values for Southern Hemisphere. But if you don't want to transfer it to geographical coordinates, if you want to use rectangular models, so you can set this flag as false to suppress this UTM projection. And you also need to give the name of interface for this to put the name on here for this interface files. Next step, you can define how many elements in this model. So here are 2 parameters to define the number of spectral elements along 2 sides of your block. And the first one, the north, first one, the direction is east and north direction. And second parameter is in the north and south directions. And you also need to provide how many MPI processors you want to use along these 2 directions. So here is an example. In this figure, they use 5 times 5. There are 25 processors they will use, and the model in horizontal direction will be divided into 25 slices. So, and in my example, I use 4 times 4. There are 16 processors I used. And one thing you need to be careful is if you use a irregular mesh, the shape of mesh is irregular, so the number of elements along each side should be 8 multiple of the number of processors along that direction. So the irregular or regular mesh can be seen in this page. So if you turn this flag as true, means you will use regular mesh. So you can see the shape of elements in your models will be rectangular. So yeah, this is the Z direction. It means this is free surface, and this is one side of your block. And you also can turn this flag off it means you will add doubling horizontal layers to coarsen the mesh. So if you turn this flag as false and then see a number of doubling layers, if I see it as 1, then you need to define the position of first doubling layer is at 11. It means started from the bottom of your model. Then the 11th layer will, the length in horizontal direction is longer than the shallow regions. So if you define number of doubling layer is 2 and the position of the second doubling layer is 9, it means in deeper region the length will become longer and longer. You also can give larger numbers like 3 or 4 or 5, then you need to define the position. You need to define more parameters in here, NZW3 and NZW4. So then you should give the material informations of your model. In this example, I give a very simple velocity model. So the number of materials, I only use 2. And the number of materials should equal to the lines in here. It means the first column is material ID, and the second column is density rho, and third column is P wave velocity. The unit is meter per second, and the shell wave velocity. And here is a quality factor Q kappa and Q mu. So because in other models, we already defined quality factor as QVP or QVS, or QVP and QVS. So you need to transfer from QVP to QS into Q mu or Q kappa. QVS is simply equal to Q mu, but QVP, you need to do some calculations and then calculate the corresponding QP, and it changes with the P and S wave velocities and the Q mu. So they are equal. So the corresponding QVP should simply equal to 1000, but for Q kappa in here, I use different values in here, and Q mu is a constant value. And for this column, is represent an anisotropy flag. 0 means there are no anisotropy in your model. And the last column here is a domain ID, which represents your model is elastic or acoustic model. So 2 means is elastic models. So if your model is very complex, you have the velocity in each element is totally different with others, then you have to write more lines. If you have 100 elements, maybe the number of materials should equal to 100, and there you should write 100 lines over here to describe these materials. Then you should fill these materials into your model. So I define 2 regions in here, and they are very simple velocity models. So it means in the east-west direction, it started from the first element of my model and ended at the last point of my model. Also in the northwest direction, it means velocities are not changed in horizontal directions. And this NZ begin, NZ end means the vertical directions. But one thing I want to mention is one represent the bottom of your model. So it means starting from the bottom of your model up to the 21st layers of your model was filled by the material 2. Material 2 relates to a higher velocity model, which means because in deeper region you should have a high velocity model, a high velocities. So this is the first region of my model, and the region was filled by the material 1, which has low velocities. And there are only 4 layers in the top 4. The top 4 layers was filled by the material 1. So you also this is for the mesh profile, and you also need to define a file for the interface of your model. For this interface data file, and the number of interface, because I only set a very simple model, so I set a interface for the free surface. So the number of interface is 1. Oh, sorry. And you need to see some parameters for this interface. False means you don't surprise the UTM projection of this interface, and the number of nodes along 2 directions, northwest and north-south and east-west directions, and the starting longitude and latitude point of your interface. And this is the spacing between nodes of the interface. And these parameters will be written in the interface1.data. Here is the interface1.data because I set a flat surface. So all of there are 4 elements in here is equal to 0. 4 means 2 times 2, 2 times 2 nodes in this file. And the layer number 25 should be equal to the number of layers in this mesh profile is 25. You also can set a very complex shape or complex interface. For example, here is a figure. If you use changing topographies in this interface1 dot file, then you can get more complex interface. So here is a figure of the model I just built. They were produced in the database MPI folder, and the file name is, this is a file name, and you should turn this flag on to save these VTK files and then find them in this folder. And you can use Parallel to open these files, and because I said program will call many processors to simulate the waveforms, and so the model will be divided into many slices. So each processor, because I used a 16 processor, is starting from 0 and then to 15. So each file or each processor will control 1 slice of your model. And there are 25 layers in vertical directions and 128 elements along each side of this model in horizontal direction. And the values in this model are represented by the material ID is simply equal to 1 or 2, which is defined in here. So after you build your velocity model, and you still need to see some main parameters in the par file of the data folder. So in this file, you should give a simulation type, just simply set it as 1 if you just simulate synthetic waveforms, because it can also do some other work like a joint or backward propagation, that kind of stuff. But for simulations, you can set it as 1, and you don't need to do noise tomography, so set it as 0. Save forward means do you want to save the forward wave field or not? if you just want to got the seismograms as a location of stations, so turn this flag as false. Still, you need to see the zone of the UTM projection, and you don't surprise the UTM projection, so see it as false. The number of processors, I just called 16 processors, so here is 16. And here is the time length of the produced seismograms. So, and the time interval of the seismograms. So you can't give a very large time interval because your simulation will become unstable. So make sure that the time interval in this parameter is small enough and which is required by this relationship is defined by the neighborhooding grid spacing and velocities in your velocity model. And if you use your defined model, so here you can set it as default. But if you want to use other model, this program also provides like one-dimensional prime model and one-dimensional. This is one-dimensional South California model, and some other models you can change it by their names. And I set boundary conditions to absorb the boundary reflected wave from the boundaries. So turn this flag as true. You also can set or cancel the boundary condition at the free surface or bottom of your model. I only use the absorbing boundary condition because the model generated by XMesh FEM3D do not support the PML boundary condition. So you need to give some parameters for the earthquake source. Still in the profile of the data of the data folder, you can turn this flag on or off. If you want to use the moment tensor source, then turn this flag as false. If you want false point source, then turn this flag on. So if you want to use moment tensor source, so you need to write for the CMT solution file in data directory. So here is this file. You should see the time of the earthquake and location of earthquakes, even name and time shift. It doesn't matter. So half duration of the source and the location of the source depth, the unit of depth is kilometer, and the moment tensor, each component of moment tensor about your source. If you don't know too much about moment tensor of the earthquake you want simulated, then you can go to Global CMT website and find the earthquake information. So here is a moment tensor. You can fill these parameters into here. And if you want to get the moment tensors based on the strike, dip, and rig information and the scaled seismic moment of the earthquake, then you can use this formula to calculate the moment tensor component in here. But they are in two different systems. You have to use this relationship to transfer XX to MRR or MTT, this kind of stuff. So the shape of the source time function this program used for elastic case is represented by the Heaviside step function. And so this is the shape of the source time function it used for half duration. The half duration of this source time function is 5 seconds. So you can define, if you don't like this source time function, you can use others. If you just define the half duration is 0 in here and then convolve your synthetics with the source time function you want to use. So then one thing I want to mention is that the 0 time of the synthetic you will got. Sorry, Chuck is here. So the 0 time of the simulation you want to get is not the real 0 time, but it's central of the centroid time of the earthquakes. So it means that there will be a time shift for the synthetics and real the observed data. So I will show an example to describe this problem. So you also need to fill the station files in data folder to show the locations of the data you want to generate synthetics. So this is station name, network name, and locations of the stations. Then the last step is to run this code to simulate waveforms. And this is the folder of our examples. Then the compiled files was in the bin folder of the root directory. So first step, you need to link all of the compiled file into this bin directory, and then simply use these 3 commands to generate your mesh and generate databases and simulate waveforms. And you need to give how many MPI processors you want to use for this command. So the last step is to see the output of these programs. So if you go to the output files, if you see it, you want to save displacement seismograms in this par file, then you will get the files ending with SEMD. And if you turn this flag on, then you can get velocity or accelerations seismograms. And these files will end with ICM-V for velocity and ICM-A for accelerations. So these files, CE means the network you define for the stations, and test 1 is the station name I just defined, and 3 component waveform E and Z. For each file, there are 2 columns. First column is time lag of this synthetics, and the second column is amplitude of displacement of the synthetics. The unit is meter. So I also did a comparison for the synthetic generated by this ICM program and synthetics generated by frequency wave number integration method, which is proposed by Lupe Zhu in Louis University. So I used the same 2-layer velocity model and generate waveforms, and the blue one, the red one is synthetics generated by this SEM program, and the blue one is synthetics generated by FK models. So we can see, at least for the radial and the vertical component, they fit pretty well, but there are some difference in the tangential component. I'm not sure why there are some difference, maybe generated by the setting of the grid size or some other factors. So as I said, the real starting time of the synthetics generated by SEM program is in here. It is a centroid time of earthquakes. So for this example, I used the top duration time of the source is 5 seconds. So it means they will have the synthetic generated by SEM will arrive 5 seconds earlier than the real one. So I gave a 5-second time shift for this model to let them fit each other. If you don't give this time shift, you will see there are some arrival time difference between these waveforms. Okay, so yeah, that's all I want to show. Yeah, thanks for your attention. Please let me know if you have any questions.
Thank you, Chuck. Dan, sorry.
Yeah. You're welcome.
But we are used to saying thank you, Chuck.
Yeah.
Chuck is here, I think.
Chuck is
I
here?
saw Chuck just joined.
Oh, he's not here. Oh, yeah. No, it's Bob.
So what do you think the differences are due in those synthetics?
You mean compared with FK method?
Yeah.
Maybe the green size I used for this SEM program or boundary condition. Maybe I'm not sure. Many factors can induce this difference.
The SH wave, the red one is for wave number, right?
The blue one is for wave number, frequency wave number.
Oh, blue is wave number.
Yeah.
Ah. Yeah, the red one is much more complicated. Something else is going on there. I would expect the blue one because the velocity model is so simple. You're just looking at a very simple SN arrival. Yeah, my apologies. It was on my schedule at 3:30. I don't know why. That's when I clicked on it.
I don't know.
You'll have to give the whole thing over. Sorry.
It's okay.
Recorded.
I'm only joking.
Yeah, I recorded if you want to review.
Tan?
Hi, Shay.
Yeah, just a simple question. Which one of these two methods do you use for your research?
For my one-dimensional synthetic waveforms, I will use FK method because this works for three-dimensional velocity models. And so it depends on what kind of problem you want to solve.
Thank you.
You're welcome.
What was the time difference between computing these two models in computer time?
The FK runs very fast. It costs about maybe 5 minutes. And this SEM method will cost a lot of time, especially when you add attenuation and the grid number of grid is, or number of mesh is very large. Then it maybe cost an hour, maybe, yeah.
Are they all run on the HPC? With
Yeah, I use HPC, yeah, to run this SEM code.
the FK also?
FK, yeah, I can run FK on my laptop. FK, I also run FK on HPC. I don't. So both of them can run. I mean, my laptop cannot work for this SEM code because it will require many cores or a lot of space, memories. But my laptop can run FK very well.
So your comparison was 5 seconds on your laptop versus
my they will cost the same time for my laptop and HPC for this FK method. I mean, there's not too much difference if I use different computers to run this code because this doesn't require too much space, memories, or there are not too much requirements for the computers for this method, FK method. Because it only works for one-dimensional velocities. You don't need to build very complex three-dimensional models. Any other questions? No. So what should I do for the record of this talk? Should I upload to somewhere?
Yeah, Tan, can you upload it in OneDrive and share with us? Yeah.
Okay, I will try to update because I didn't use the OneDrive before.
Okay.
Yeah.
You can find it from the Outlook apps.
Mhm.
You can,
Okay, yeah, I will try.
it's very easy.
Okay, I will try.
Thank you.
You're
Nice talk.
welcome.
Thank you, Mr. Tan.
You're welcome. Okay, if there's no questions, we should end. So yeah, thanks for coming this meeting. Yeah. Okay. See you.
See you.
Bye.
Goodbye.
See you. Bye.
Bye.